Okay, in this video we're going to be taking a look at 16.3, which is about the fundamental theorem of line integrals. Okay. So I have some motivating examples up here on the board. What I've done is I've written down two force fields, F, which is 2xy squared, 2x squared y, and G, which is just x, xy. Okay. And then I've created these two curves that both connect the same starting and ending point. They both go from the origin to the point 1, 1. Curve 1 is just the straight line, so I parameterize that as R1 of t is just t, t, and of course t is just varying from 0 to 1. I suppose I can write that in. Okay. R2 of t, this is part of a parabola, so that's the point t, t squared, and again, t is varying between 0 and 1. So I've got two different paths, but that take me from the same starting point to the same ending point. Now what I want to do is calculate four work integrals. I want to calculate the work integral of f along curve 1, the work integral of f along curve 2. Then I want to do the same thing with g. I want to calculate the work integral of g along curve 1 and g along curve 2. So I'm going to go ahead and work those out. I would suggest that you pause the video, work them out on your own, and then turn it back on and check in to make sure that we got the same answers. Okay, welcome back. Okay, so if I wanted to do the integral along curve 1 of f dotted with t ds, okay, I know that's going to become the integral from 0 to 1. I'm going to just write f in terms of r1 of t, which I've parameterized. So x and y both just become t. So this is going to become 2 times t squared is 2t cubed, comma, 2 times t squared times t is another 2t cubed, dotted with, now what goes here is r1 prime. Well, if r1 was just t, r1 prime is just going to be 1, 1. So we are integrating from 0 to 1, 2t cubed plus 2t cubed dt. That's the integral from 0 to 1 of 4t cubed dt. That's just going to be t to the fourth evaluated between 1 and 0, which is 1 minus 0, which is 1. Okay. So we simply got 1 when we integrated f along curve 1. Fabulous. Okay, let's do it along curve 2. I'm going to just record that this result was 1, but clear my workspace. So that was 1. Now I'm going to do along curve 2 the work integral that I get here. So I know that's going to be the integral from 0 to 1. Now I'm writing f in terms of r2 of t. So x becomes t, but y becomes t squared. So this is going to become 2 times t. T squared squared is going to be t to the fourth. So that's a 2t to the fifth. And then that's 2t squared times t squared is 2t to the fourth. And then what we're dotting with is r2 prime of t, which is just going to be 1, 2t dt. So we're integrating from 0 to 1, 2t to the fifth plus 4t to the fifth dt. That's integrating from 0 to 1, 6t to the fifth dt. That's lovely, because that's just 6t to the sixth over 6, so that's t to the sixth from 1 to 0. That's 1 minus 0, and that's 1. Okay. So we got, even though we took a different path, we actually got the same answer. Okay. So when we integrated along curve 2, we got the same work was done by this force field. Okay. Now essentially what happened there is obviously C2 is the longer path, but along this path, if I were to look at this force field, the force is contributing less along this longer path to the work that's being done, whereas the force vectors on this shorter path are contributing more to the work that's being done, so we end up with the same amount. So that's a kind of interesting result. Two different paths with the same starting and ending point, and we get the same amount of work that's done. Okay. So the question is that coincidence or not? The answer is, it's not coincidence. But it doesn't always happen for all work integrals. So let's take a look at what we get with G. Okay. So I'm going to erase my work for F here. And let's take a look at G. So if I integrate along curve 1, G dotted with T ds, I know that's going to be the integral from 0 to 1. Now I'm going to write G in terms of R1 of t. So x and y both just become t. So that's going to become t squared. And we're dotting with R1 prime of t, which we saw earlier was just 1, 1. So we're going to get the integral from 0 to 1 of t plus t squared dt. That's going to be t squared over 2 plus t cubed over 3, evaluated between 1 and 0. So that's 1/2 plus 1/3 minus 0. So let's see, that'd be 3/6 plus 2/6. That's going to be 5/6. I'm not crazy about this marker. I think I'm going to switch. Okay, so that gave us 5/6. Let's keep that result up there, but now work and see what we get along curve 2. Okay, so if I look along curve 2 of the work integral I get with G, I know that's going to be the integral from 0 to 1, and I'm going to write G in terms of my parameterization of curve 2. So x becomes t and y becomes t squared. So let's see, I'm going to get t and then t cubed dotted with, we're dotting now with R2 prime of t, which is just going to be 1, 2t. So that's going to be the integral from 0 to 1 of t plus 2t to the 4th. So that's t squared over 2 plus 2t to the 5th over 5, evaluated between 1 and 0. So that's 1/2 plus 2/5 minus 0. So let's see, that's going to be 5/10 plus 4/10. That's going to be 9/10. So when I worked with this force field, I do not get the same work done using different paths. So sometimes we do, sometimes we don't. But I said it wasn't a coincidence that we got the same thing when we worked with F. And the key is that F is a conservative force field. Now, what does it mean to be conservative? We must rack our brains. To be conservative, that means that it's the gradient for some potential function. Okay. Now I'm just going to tell you right now what a potential function is. As we work through this section, we're going to figure out, how do we figure out when something is conservative, and if it is, how do we find a potential function? We haven't learned that yet, so right now the teacher gives it to you. So if I take f of xy, and I let that be x squared y squared, if I were to take the gradient of f, which would just be f sub x, f sub y, that's going to be 2xy squared, 2x squared y. That's exactly what f is. Now, G is not conservative. Again, at this point, I simply have to tell you that, okay? We will eventually be able to see how we can tell that G is not conservative, that there's no function, so that if I take the gradient of that function, I will get G, okay? But that's the significance here. f was conservative, and in the next video we'll actually state the fundamental theorem of line integrals, which essentially says if you do a work integral with a conservative vector field, the result is independent of path. You're going to get the same answer regardless of which path you take to get from your starting point to your ending point.